Okay. So with this, we're going to start talking about the hemoglobin dissociation curve. And this is one thing that, don't want to scare, just pay attention. I'll do my absolute best and ask me as many questions as you need, because this is the foundational concept in the respiratory physiology. And as soon as you grasp it, everything else is easy. Okay? It's probably the hardest concept that we talk about in this little game. So this graph shows you so-called hemoglobin dissociation curve. Okay? In order to read the graph, first we need to define the axis. So here's the x-axis, right? And it shows you the partial pressure of oxygen in the lungs, and the tissues, and the blood. Doesn't really matter. Partial pressure of oxygen. Does that make sense? Well, we leave it to the lungs or tissue. Y-axis shows you the saturation of hemoglobin. You can say, wait a minute. Molecule of hemoglobin may have 4, 3, 2, or 1. Essentially, if 4 is 100%, then 3 should be 75. 2 molecules of... Am I confusing? No? So, this should be 100%, right? This is 75. This is 50, and this is 25. How can we get, say, 43? Well, you have to understand that if we take a single molecule of hemoglobin, those are only, well, or nothing, right? Only 5 states it can be present in. But if we take all molecules of hemoglobin, some of them going to have 4, some 3, 2, 1, so on and so forth. We're clear? So when we talk about hemoglobin saturation, we refer to like gazillion molecules. We're good? So we're going to first talk about 2 points. The warehouse, which is lung, and the tissues, which is the department store. Let's talk about lungs. The partial pressure of oxygen in the alveoli is high, right? Therefore, the partial pressure of oxygen in the blood is high as well. Concentration of oxygen in the blood overall is high, 100 millimeters. At this concentration, it turns out practically all hemoglobin is saturated. Are we clear? So we are in the warehouse. There are a lot of goods. All trucks are loaded. Now I want to specifically highlight one thing. This curve is not sort of a mathematical graph that can be deduced from something. This is what we observe in people. Does that make sense? That's what it looks like. If you measure, that's what we're going to measure. Am I clear? So don't try to say, what is the equation that describes this curve? There's none. It's the observation. Make sense? Now think about this. Those trucks, loaded trucks, they go to the tissues. Partial pressure of oxygen in the tissues is 40. We know that because we measured it. And we measure hemoglobin saturation in the blood that runs through the tissues and leaves them. Kind of think about this. Blood at this moment, it leaves the capillary beds in tissues and enters veins. Are you comfortable with it? Turns out that hemoglobin saturation is about 75–77%. Which is really a lot, if you think about this. Using our truck analogy, imagine this. You have a fully loaded truck. It arrives at the department store, unloads a quarter of all goods comes back to the warehouse. Is that clear? Just this observation. Now, what is the percentage of hemoglobin? What is the percentage of oxygen that got unloaded in the tissues? Can you tell me, how can I show it on the graph? What should be it? It should be difference, right? Between what? Truck analogy, people. It should be difference between the warehouse, the store, lungs, and tissue, right? So in the lungs, 100% saturation. In the tissues, let's say 75. This difference, 25%, is what gets into the tissues. If we translate it to normal people language, we can say that only quarter of all oxygen that is carried by hemoglobin reaches tissues. Does that make sense? Only quarter of all oxygen actually gets in the tissues. Now, what are the physiological implications of it? They're quite important. So look at these two happy people. This gentleman is, say, Hawaii. And this lovely lady is in Colorado. Okay, you follow me so far? So Hawaii is, well, I'm talking about the beach, obviously. So this guy is at the sea level, like absolute sea level, right? Here. So oxygen concentration in the air is as high as it ever will be. The oxygen concentration in the lung is high as it ever will be. And this is the point where practically 100% of hemoglobin is saturated. That makes sense? That's partial pressure of oxygen in this gentleman's lungs. Do you follow me? Now say this lovely lady, let's say it's his wife, okay? They spend vacations separately, nothing unheard of. So she's in Colorado. She is at the elevation of, say, 10,000 feet, okay? What happens with oxygen concentration in the air at this elevation? It decreases. Very well. The amount of oxygen in the atmosphere decreases. What happens to the amount of oxygen that actually makes it to the blood? It decreases. So partial pressure in Colorado, oxygen concentration in the blood of this lovely woman is now 80. That makes sense? That's her lungs. Does that make sense? However, if you would look at the saturation of hemoglobin, it marginally goes down from, in this case, 98 to 95. Because that's what we are. That's the feature. Does that make sense? What is the physiological importance of it? Think about this. If you climb up, if that would be not a curve, but a line like this, okay? Then if you go from 100 millimeters of mercury of oxygen to 80, your saturation of hemoglobin falls from almost 100 to, I don't know, 75. Does that make sense? This specific shape here, this plateau on top of the curve, allows you to still have good saturation of hemoglobin when oxygen levels drop. Does that make sense? So basically, when you go how people climb Mount Everest. They climb to the first level. They don't die at 3,000 meters. They don't die. They adapt. Then they climb, go next level, the base camp. They adapt. They go next level, the base camp. They adapt. And then from about like 6,500, they climb last 2 kilometers, and then they die. So that's terrible, okay, if they by themselves. But nevertheless, they can do it. Because drop in oxygen concentration, even without any adaptation, does not very much affect the hemoglobin saturation and oxygen transport in the blood. Do I make sense? Are we clear about it? That's really important. Another implication. I have normal saturation. I got checked by a doc last week for a strep infection. So I had 95. Okay? This means that even if I will breathe really deep or breathe pure oxygen, I'm not really going to increase the hemoglobin saturation. Does that make sense? I can, if we continue the curve, it'll go maybe like this. So I can get to, 120, 140, and I will still be at about 98, 99% saturation. You can't go above 100. Does that make sense? It's kind of an interesting consequence. To Joseph's question, what happens when oxygen concentrations drop? There is a certain level at which, we're not going to be able to breathe. We're not going to be able to survive. But you can see that there is some drop in concentration of oxygen in the air that will allow us to survive. Okay? Now, what about unloading? Let's look at the unloading. Remember, only what we suggested, like 25, 22% actually get unloaded, right? That's at rest. This is rest. Okay. When we start to perform a vigorous exercise, what happens to oxygen concentration in tissue? It goes down. Why? When we work out, what do we work out with? Which tissue? Muscles. So when we work out, muscle metabolism increases. Muscle metabolism is largely aerobic. Muscles start to consume way more oxygen, and they go from 40 millimeters of mercury to 20 millimeters of mercury in the muscles. Do I make sense? It turns out at this oxygen pressure, unloading of hemoglobin increases dramatically. Does that make sense? So when hemoglobin reaches the active muscle, instead of unloading 25%, it unloads 60%. Using our department store analogy, your 25% unloading is the unloading on the regular day. The truck comes in, unloads only what's needed, and goes back to the warehouse. 60% unloading is the Black Friday. They come in, they see that shelves are empty, they unload much more, and go back to the warehouse. We're clear. Do you understand that? So in metabolically active tissues, oxygen partial pressure decreases, oxygen partial pressure decreases, unloading increases. Unloading. Are we good? Now, the best trick is that you don't need to load more. All you need to do is to unload more. Does that make sense? You don't need to try and stuff your truck with a ton of extra goods. You already have them. You just need to drop more. That makes sense. Actually, this reserve, called venous reserve, is really important. When people say stop breathing, heart stops, something happens. Circulating blood has enough oxygen to maintain brain for about 1 to 2 minutes. Okay, so that's sufficient to maintain the brain function for about 1 to 2 minutes. Does that make sense? Now, what influence? So this purple one is the typical dissociation curve. Now, let's talk about factors that influence loading and unloading. It turns out it's incredibly simple, because unloading increases in active tissues. Now look at the picture on top, right upper corner. Okay, so this red one which I highlighted is the normal curve, right? 38 degrees Celsius, practically body temperature. Okay, so and this is going to be 40 millimeters of mercury. Okay, now what's going to be unloading levels? So that's the saturation in the lungs, the dashed line on top. Can you see that? I just pictured it. And this huge dot here shows you the unloading point at 40 millimeters of mercury. Am I clear? Can you see it? You're okay with it? Okay, I'm going to ask you multiple times about it. So the unloading is going to be this double-edged arrow. Can you see it? Now, look at the purple line, which corresponds to 43 degrees Celsius, higher temperature. The unloading is going to be this blue double-edged arrow. Can you see it? Do you understand why is that so? Because that's the difference between the saturation line and the unloading level at the same partial pressure. What it means is that elevated temperature increases unloading, shifting the dissociation curve to the right. Decreased temperature decreases unloading, shifting the curve to the left. That makes sense? A couple more. CO2, hydrogen ions. This is called a Bohr effect. Turns out that if pH or CO2 concentration increase, unloading increases as well. Look at the right bottom picture. So this is normal, okay? This is your 40. Okay? This is 100. So this is unloading at the normal pH, normal CO2 concentration. This is going to be unloading at the lower pH or higher CO2 concentrations. Can you see that? So, high CO2. Again, elevated levels of carbon dioxide. or higher acidity / lower pH shifts the dissociation curve to the right and increases some loading of oxygen from hemoglobin. It all sounds pretty, I know, all sounds pretty, how to say, dry. Now think about this. What are the 2 points in respiratory, in respiration, external and internal, that we really care about? Lungs and tissue. What happens in tissue? And let's talk about metabolically active tissue. During metabolism, what happens to oxygen? Oxygen levels go, metabolism in the tissue. Think tissue is using oxygen for ATP synthesis, oxidative respiration. So oxygen levels go down. Oxygen is used to burn carbohydrates, producing which gas? CO2. So CO2 levels go up. And during oxidative respiration, what happens to the amount of hydrogen ions? Amount of hydrogen ions increases, acidity increases. Does that make sense? So, metabolically active tissue. Oxygen down, CO2 up, pH down. Does it make sense? Now, when all this happens, what do we need to do? How do we need to change that loading? We need to increase it, right? Because tissues need more. They're metabolically active. Those signs, hey, my oxygen is low, my CO2 is high, my pH is low. I need more oxygen. Please increase the unloading. Does that make sense? Oh, by the way, metabolically active tissue, what about the temperature? It goes up, right? So now we have temperature, CO2, and pH, and oxygen. 4 factors that regulate the unloading. So metabolically active tissue are warm, deoxygenated, carbon dioxide rich, and acidic. Lungs are oxygenated. Think about alveoli. A lot of oxygen, not a lot of CO2. They pretty cold compared to the rest of the body. Air that we inhale is, 68, 70, whatever. And turns out they're not acidic at all. They're actually more basic. So lungs are opposite to metabolically active tissue, which makes perfect sense. Because lungs is the last place you need oxygen to be unloaded. You do the opposite thing. Does that make sense? So basically, that hemoglobin dissociation curve, if we go back to the upper picture, this effectively will be hemoglobin dissociation curve in the metabolically active tissues. This will be hemoglobin dissociation curve in the lungs. Do I make sense here? Do you see this shift? Okay? That makes sense? The effect which, when unloading of oxygen depends on the CO2 and pH. It's called Bohr effect. Okay? Higher concentrations of CO2 in the tissues promote oxygen unloading. Now, when people are hypoxic, what can cause it? Hypoxia is not just low oxygen in the air. It's actually low delivery to tissues. Hypoxia can be of different sorts. It can be anemic. When red blood cells are low, or hemoglobin is low in the red blood cell. I think it's called mean hemoglobin concentration or something like that per cell, and it decreases. Ischemic hypoxia, obviously, no blood supply. Histotoxic hypoxia is fascinating. And cells cannot use CO2, not use oxygen. Cells, what do they use oxygen again? Remind me. Which process do cells use oxygen for? Come on. What living organism use oxygen for? R word. Respiration. Yes, they use it for oxidative respiration. Right? All that. Glycolysis, Krebs, and other nightmarish names. There are poisons that inhibit these processes. One of the most notable is potassium cyanide. I honestly don't know the mechanism, but it inhibits oxidative respiration, some step there. So cells cannot use oxygen. Oxidative respiration in cells virtually stops. And it's absolutely fascinating because person starts to suffocate. Cells do not get oxygen, so symptomatically it's like suffocation without actual suffocation. And interestingly enough, if you would look, now one question that I like to ask at this point, if you would look at the oxygen concentration in cells, cells cannot respire. Oxygen concentration in cells, is it high or low? Okay, oxygen concentration in cells and in the blood, is it high or low in poisoning by potassium cyanide? That's sort of a trick question. Giving you a hint, it's counterintuitive. Huh? It's extremely high. Because when cells cannot use oxygen, the first physiological response is to breathe it in. So amount of oxygen in the blood is at its historical highs. That oxygen gets in the cell, is not used there, stays there basically. Person continues to breathe and eventually dies of suffocation. There was a pretty famous case of it when a bunch of Tylenol bottles, 70s I think, in Chicago, were laced with the cyanide, were sold, and quite a few people died actually. And the person who did that was never found. It's one of the unsolved mysteries. So that is toxic hypoxia. Hypoxemic hypoxia, problem with the ventilation. Okay? Lungs don't work. Chronic obstructive pulmonary disease, asthma, it's all hypoxia. Right? Now, specifically, carbon monoxide poisoning. The reason why we have carbon monoxide detectors in the houses is that it's a silent killer. There's no smell, no color, and it can kill you pretty quick. Okay? There was a case recently in Britain, 2 people died because of carbon monoxide poisoning in their house. There were still, people still... Authorities, police investigates what happened, but basically they died in their sleep. What happens during carbon monoxide poisoning? Carbon monoxide, CO, can bind to the same place in hemoglobin that oxygen binds to. The main problem is that it binds 200 times better. Does that make sense? So if we would compare the rate at which saturation with CO occurs, it's going to be basically 200 times faster. So when a person starts to inhale carbon monoxide binds to hemoglobin, and oxygen cannot unbind it back. Does that make sense? And the only treatment actually for a person who experiences carbon monoxide poisoning is to get this person out in the fresh air and possible, give this person oxygen. Because at this point, high oxygen concentration will really, really help. Okay? Much higher than in the air. Now, interesting feature and symptom, I hope nobody will ever have to use it. Just so you know, when CO and carbon monoxide binds to hemoglobin, it forms essentially the molecule called carboxyhemoglobin, which is bright red. People who experience carbon monoxide poisoning, their palms and their faces turn bright red, unnaturally red. Okay? It's one of the symptoms. Check. That makes sense. We're comfortable about this stuff. Okay. Because now we're going to switch from your most lovable subject, physics, to your second most lovable subject, physical chemistry. So we're going to talk about the transport of carbon dioxide in the blood. With oxygen, everything is really simple, honestly. You have hemoglobin, oxygen binds to it in the lungs, unbinds in the tissue. That's it, really. Right? It's simple. The problem with CO2 is that it doesn't really bind to hemoglobin that well. So there are three ways to transport CO2. It can be transported just dissolved in plasma as the CO2 molecule. It can bind to hemoglobin. About 1/5 of it binds to hemoglobin, forming carbaminohemoglobin. And 70% transported as bicarb. And this is the reaction that forms bicarbonate ion. Did you see it before? I bet you did. When we did gastrointestinal system, we saw this reaction in parietal cells, stomach, and that's acinar cells of the pancreas. Right? So again, and before we move on, I every time I kind of wrestle with myself, should I talk about this, should I not, about chemical equilibrium. So this time I decided I will. And I will try to be as simple as possible, and it's really sort of common sense idea. Imagine that you have a reaction. A plus B produces C plus D. Okay? I'm going to be talking about only like this direction. So this reaction will be at some point in the balance, right? All reactants that could interact, they did, and they produced the products. You good? Now, what if we want to make more products? What should we do? There are two options. Option number one is to add more reactants. Option number two is to start getting rid of the products. So, kind of, oh crap, we don't have any products anymore. Let's run the reaction more. Let's shift the balance to the right. Does that make sense? Think about it as like teeter-totter again. Okay? Does that make sense? So, like a tug of war, if you want, some effort from this side, you need to start pulling on the rope. Okay? Same is applied to the reverse reaction. In order to get more A plus B, we need to accumulate C plus D. Does it make sense? Do you understand that basic chemical equilibrium? So, let's talk about chemistry. First process, super simple. Super simple. CO2 is dissolved in plasma. That's it. 7%, we got rid of them. Okay, we're good. Cool? Number 2. Carbon dioxide slowly interacts with water, forming carbonic anhydrase, and it dissociates in bicarbonate ion and proton. Does that make sense? Now, how can you shift the balance to the right? What you have to get rid of? What 2 options you have to get rid of? Those are products. Those are C and D, right? What you can get rid of. You have to pick bicarbonate or proton. Bicarbonate doesn't really work, but what we can do, we can take proton and bind it to the proteins of plasma. The basics of proton will interact with plasma proteins. You essentially take it out. Does that make sense? So this binding of hydrogen ions to the plasma proteins facilitates the reaction to go this way. You understand? Additional thing that facilitates the reaction here, you have a lot of CO2. Just a lot. So basically you provide a lot of reactants. Make sense? We good? Think about this. If you experience metabolic acidosis, which means you have a lot of hydrogen ions that come not from that respiration thing, I don't know, you drank like 2 gallons of acid. Okay? Or you're diabetic and you didn't take insulin for like 3 days. Okay? In this case, hydrogen ions here will start to accumulate because buffering capacity of those proteins is limited, right? And CO2 will be accumulating in the tissues, essentially. Does that make sense? Good? So you're comfortable with this? Left and right, a lot of CO2 taking out hydrogen. We good? Good? Okay. Now let's take a look what happens in the red blood cell. In the red blood cell, one option is to bind carbon monoxide to hemoglobin, forming carbaminohemoglobin. Good? That's it. That's like really simple. That's it. We're done. We're done here. Okay. What facilitates this reaction? Just the sheer amount of CO2 in the beginning. Now, the most important part is right here. And for me, it's fantastic chemistry. CO2 inside of the red blood cell, and I want to specifically highlight it, inside of the red blood cell, very quickly reacts with water. Can you see this reaction? Circle it right now. Reacts with water. Why it reacts very quickly? Because there is an enzyme in the red blood cell called carbonic anhydrase that facilitates the formation of carbonic acid. Carbonic acid, the same way it did in the plasma, dissociates to bicarbonate and the proton. Do you follow me? Now, bicarbonate gets pumped into the blood, which is awesome, really. So we get rid of one product, shifting the equilibrium to the right. Do you follow me? And now this is my favorite. This is for me like a climax of this whole thing. Hydrogen ion binds to hemoglobin. Because in plasma, hydrogen ion, look at the picture. What does it bind to? It's written there. Tell me, just read it. Huh? Plasma proteins. What is the most common protein in red blood cell? It's in red blood cell. It's going to bind to albumin. You're absolutely right. In the plasma. In red blood cell, it's going to be. What's the most common protein in red blood cell? Hemoglobin. So this hydrogen is going to bind to hemoglobin. That's not the climax. We're like Everest is 8,848 meters. We are 8,800. We have 48 meters to climb. Okay? Here's the deal. Hemoglobin carries oxygen, right? And what we look at here, this is tissues. What happens to the oxygen and hemoglobin in tissues? Oxygen leaves hemoglobin and gets there, right? So it basically is a reaction shown here. Oxygen and hemoglobin. You want to facilitate this reaction. Shift it to the right. Am I clear? When hemoglobin binds with hydrogen, you basically take hemoglobin away as the product. You provide an additional shift to this reaction. You facilitate the unloading. So far, it's a little bit overwhelming. Now let me tell you something. Imagine that you have a tissue with a lot of CO2. A lot of CO2. And I want you to focus specifically on the formation of bicarbonate inside of the red blood cell. So we have a lot of CO2. What happens to the levels of carbonic acid if you have a lot of CO2? They go up. Levels of hydrogen ion that is produced go up. So if you have more hydrogen ion, it can bind more hemoglobin, which shifts the unloading reaction towards the unloading itself. Does that make sense? It turns out I just showed you how elevated levels of carbon dioxide increase chemically unloading of oxygen in the tissues. Does that make sense? Good? It's pretty neat, I think. That was Everest, Mount Everest. Just here. Okay? Now, this all happens in the tissue. We're good? So that's tissue. Tissue. Now, next we need to talk about, it's tissue. It's kind of a little bit of a explanation what's going on. Screw that. This is lungs. So in the lungs, what do you need to do with carbon dioxide? From the blood to the alveoli, right? Here's what happens. First of all, concentration of CO2 in the blood at this point is much higher than, well, not much higher than in the alveoli. So it shouldn't be a big problem, right? CO2 that was just dissolved moves to alveoli, no worries about it. Now, CO2 here diffuses into the alveolus. Why does it diffuse this way? It's a very simple question. Concentration gradient. Because CO2 concentration in the blood is higher, right? What you do, you basically remove a product away from the reaction, and you shift this whole reaction, this one, to the left. Are we clear? Okay, so we got this part. Carbaminohemoglobin dissociates again because CO2 constantly diffuses to the alveoli due to the concentration gradient and shifts chemical equilibrium this time to the left. And finally, the most important part is here. Okay? This proton binds to bicarbonate. This whole thing goes to the left. But not only this. Think about it. It's a balance, right? So as this proton here is trapped by bicarbonate, it is actually forced with this reaction going to the left. It is forced to leave hemoglobin. It provides free space for oxygen to bind. Does that make sense? That's pretty neat. Okay. Now, any questions before you talk about holiday? Okay. So, for mechanisms, make yourself comfortable with the hemoglobin dissociation curve, please. I'm going to ask questions about it, shifts and all. It's much easier than you think. No, seriously, it's much easier than you think. Draw it. I think I posted respiratory worksheet. Did I or did I not? Did I post? Okay, I'll post respiratory worksheet. It's rather small, but it contains the drawing of the dissociation curve. Just play with it. You know, like, try to explain it to yourself. That's more of a point. No, it's really, if you want, I'm serious, if you want, you can tell me, can I explain it to you? I'll be happy to hear. Seriously, like, if you want, I know some of you come in here early, we can arrange the time. I'm just in the office. Don't hesitate to come to the office and just pull me out. Say, let's do the dissociation curve here on the board. I'll be happy. Okay? Good? This, I'm going to ask you about the mechanism of CO2 transport. What happens there? What hydrogen binds to? What happens in the lungs? What happens? Yeah, proteins, basically. What happens in the tissues? Can CO2 bind to hemoglobin? Yes, it can. Oh, by the way, important sort of a note. Imagine that this is molecule of hemoglobin, 4 subunits, okay? This is heme. Okay? So where would oxygen bind in this molecule? Heme. Oxygen is going to be blue. That's oxygen. Where would carbon monoxide bind? Also heme, yeah? Carbon dioxide. Turns out it binds a protein. It has nothing to do with heme. It binds. So this is going to be your carbon dioxide. Does that make sense? So carbon dioxide and oxygen, they do not compete for the same space. Got it? Okay. So, Haldane effect. When carbon dioxide concentration increases, then more carbaminohemoglobin is going to be formed. Carbaminohemoglobin molecules, they bind hydrogen more effectively Okay? And that leads to the decreased hemoglobin saturation. Let me go up. So more carbaminohemoglobin, wait a minute. Yeah, more carbaminohemoglobin means that hydrogen binds to it more effectively. Okay? If it binds to it more effectively, then this hemoglobin will be also taken out of consideration. Unloading of oxygen will increase, and unloading of oxygen leads to lower oxygen concentrations in the blood and decreased hemoglobin saturation. Okay? Which actually means that CO2 concentration in the blood goes up. Sort of a progressive effect. As amount of CO2 in the tissue increases, CO2 transport from the tissue increases as well. Okay? Which leads to more effective exchange of carbon dioxide in the tissue and in the lungs, and essentially we expire CO2 much more effectively. Does that make sense? In general, in terms of the respiratory system, let me tell you something. For regulation of respiratory function, carbon dioxide plays much higher role than oxygen. I'm kind of telling you this ahead of time. Did you swim underwater? I mean, ever. Like, just you dive and you swim underwater. I'm not talking snorkeling. I'm not talking like anything hardcore, you know? If you ever try to swim as far as you can, you know that there is a point you realize, holy crap, I need to breathe. So you get up and you take this breath. The deal is, it doesn't happen because your blood runs low on oxygen. It happens because your blood runs extremely high on CO2. It is very hard to run low on oxygen. Why? Huh? Speak up. Because we have that venous depot, that left over, that 75%, that is really hard to get rid of. Does that make sense? So it's incredibly hard to run low on. Your tissues are going to be oxygenated. But when CO2 levels increase, that is what sends signal to inhale. Basically, what I'm trying to say is why people drown. When they cannot get to the air, at some point, and yet they understand they shouldn't breathe underwater. What happens? The reflexes overrun the conscious control of the breathing, and they reflectory inspire. And the water gets in the lungs. Does that make sense? Oh, I have a wonderful 20-page review on the physiology of drowning. It's extremely interesting. It's super interesting. There's so many systems involved. Now, this is called, carbonic acid bicarbonate buffer system. It's the most important buffer system in the blood. Why? So if blood becomes more acidic, okay, then that extra acid, let me write down there. Got it? There's a poorly written, but sort of. So if hydrogen becomes high, acidic, acidosis, the whole balance, you make more reactants, the whole balance shifts to the left. Amount of carbonic acid increases, and we exhale extra acid in the form of CO2. That makes sense. If this becomes low, then carbonic acid that we have dissociates and produces more hydrogen ions. Does that make sense? Good. Now, the alkaline reserve is extremely important. If you have a good, decent alkaline reserve, it stabilizes your blood pH better. Okay. Now, we can change the blood pH, the respiration. I want to specifically highlight that our respiration changes when our requirements for oxygen change. That makes sense. So now I don't need much oxygen, so I breathe normally. If I will start running, I need way more oxygen. My breathing rate and probably depth will go up. We clear? However, you know how people hyperventilate? Hyperventilation is when the amount of air that is inhaled and exhaled is much more than the actual physiological needs for the organism. So what happens in the hyperventilation? Here at the bottom, rapid deep breathing. We exhale CO2, just a lot of it. When we get rid of CO2, we get rid of acid. When we get rid of acid, blood pH increases, which is actually quite fun because elevated blood pH stimulates the neuronal activity, which can manifest in normal people as unconsciousness. In people with epilepsy, it triggers epileptic bout. Okay? Yes? I was expecting this question. First of all, I think you realize you look absolutely stupid and you calm down. Physiologically, there's a lot of sense in it. Think about this. When you exhale, the concentration of CO2 in exhaled air is high. Oxygen concentration is low. When you exhale in the bag, you concentrate CO2 in this bag. And when you keep breathing this air, you bring back that CO2 back into your blood, which prevents hyperventilation, prevents overactivation of neurons.
So it keeps your pH normal?
Yes, it keeps your pH normal. And think about this, when you are super excited, whether, like you're super stressed, you do this, your neurons are already hyperactivated. When you breathe in the bag, you at least keep pH normal, or maybe lower down a little bit. Lower pH will decrease the neuronal activity. Does that make sense? And another thing about this, I'm going to finish with this one and we'll let you go. Another thing about this buffer thing, respiratory system tries to compensate for metabolic changes. People who have metabolic acidosis, diabetics, okay? When they have metabolic acidosis, they will try to get rid of that acid. Not consciously, don't get me wrong. It's not like, oh crap, my pH is like, blood pH is 7.3. I need to get rid of that acid. I'm going to breathe faster. No, this response is triggered in the respiratory centers, in the pons and the medulla, and the breathing rate immediately increases. Does that make sense? No. Usually, if the source of the metabolic disturbance remains there, you cannot get rid of it. You cannot get rid of hydrogen. That make sense? Questions? Okay. Let me pause there.